Hi everyone, my name is Marianne and I'm responsible for the training coordination at Hardent. I'd like to welcome you all to the final of our fall webinars, and we're pleased to see that so many of you are able to join us today. I'll shortly be passing over to our presenter, Tim Corcoran, who will be giving you an intro to UVM. Tim will present for about 50 minutes and then we'll wrap up with some of your questions. This is a great opportunity to ask him anything you've ever wanted to know about UVM. Please go ahead and submit your questions throughout the webinar using the questions box. Tim will then answer as many questions as time permits. I hope you all enjoy the webinar, and I'm now passing over to Tim, who will begin.
Hello, everybody. My name is Tim Corcoran, and that's my smiling visage at the bottom of the screen there. I'm a verification specialist at Willamette HDL. We're a company based in Beaverton, Oregon. But we're training partners with Hardent, and that's how I'm here. I'm the co-developer of our System Verilog and UVM training materials in our classes. So I'm the ideal person to talk about the register transfer layer, or the register access layer. So let me tell you a little bit about Hardent, if you're not familiar. Hardent is a company based in Montreal, Canada, with a team of experienced designers and other engineers that can offer a number of different services from on-demand technical support through training, of course, that's why we're here, and IP product development as well in various areas, as you can see here. Hardent offers, in terms of specifics of the training, Hardent offers training courses in the FPGA arena, whether that's FPGA design, Xilinx design methodology, or the Vivado design suite. From that, of course, you can tell that Hardent is a Xilinx authorized training provider. Independently of Xilinx, we also offer verification training in System Verilog and UVM, some new training coming online shortly in Portable Stimulus, PSS, and also System C and other languages. There's DSP training, high-level synthesis and DSP design, embedded systems design, various languages, as I mentioned, and also some connectivity classes as well. For information about our training courses, you can just visit hardent.com/training. All right, so we're here today to talk about one aspect of the UVM methodology, and that's the register layer. Excuse me, also sometimes referred to as the RAL, the register access layer. I'm going to talk about this in three sections, or in three different ways. The first way, as it's shown here, part one, is how do we model the registers within our design? How do we model it? Because this is the model that will be used as an access layer on top of our design. Then the second part we'll be talking about how you integrate the model once it exists with the design, the typical UVM style test bench that you've already developed. And then thirdly, I'll talk about how you actually use it, what APIs exist for you to access the registers within your design through the convenience of the UVM register layer. So let me start at the very beginning in case there's anybody in the audience who's not terribly familiar with UVM itself, and say that it's a large source code library written in System Verilog that you can use to basically hit the ground running, okay, to help you get up to speed as quickly as possible doing system level verification. So it's a large library, many thousands of lines of code, pre-tested, pre-debugged, etc., with a bunch of base classes that you can extend from. The UVM library is defined within a System Verilog package called the UVM package. The class, it consists of class declarations, static singletons. If you're not familiar with a singleton, that's a special class that can only be instantiated once, but is visible throughout the entire design or test bench hierarchy. It's a way of exposing certain core features in an easy way for everybody to be able to reach and manipulate them. Then there's a set of convenience methods, which are sort of like the singleton in a sense that they are, you don't have to know where they're defined. You can access them as if they were global, but they give you a very convenient way of accessing the UVM library, generating messages, things like that. So a typical test bench component, a piece of your test bench, will be extended from some base class in the UVM package. You might want to write a scoreboard, so you say my scoreboard extends UVM scoreboard, which of course is a class in the UVM package. We also sometimes instantiate classes directly from the package. And we can access the static singletons in the package, such as the factory. If you're familiar with the factory pattern, UVM offers the support for the factory pattern in System Verilog. And of course, because the UVM package defines some methods at the top level, they are effectively visible to us as if they were global, and that's where a lot of the convenience methods are available. All right, so that's a 50,000-foot view of UVM, but let's see what a test bench looks like. So let's say we were testing a new memory subsystem that's going to sit on the AHB bus. So we might define a module called HDL top that contains our device under test, our memory, and we would define a System Verilog interface block to do the interface accesses for us. Now, it's worth mentioning that this is a System Verilog interface block, but it's a special kind, my favorite kind, which is the bus functional model style. This allows us to have a number of tasks within the interface that cause the traffic to occur on the AHB bus. So for example, we might have an AHB write task, an AHB read task. The beauty of this is all of the bus protocol IO is concentrated in this interface, which means it doesn't mess up our nice other block here. HVL top is a module that contains nothing but System Verilog object-oriented code. So in a typical UVM test bench, we divide the top level into two. The one on the right is all RTL or similar level of code, and the one to the left will be nothing but object-oriented UVM code. The test class will exist, and the test class will create the environment class. And in the environment class will be a set of agents. Well, I'll talk about agents again in a few minutes, but basically an agent is a conglomeration of all of the pieces that are needed to talk intelligently to the device across the target bus. So there'd be one agent for each interface on our design. In this case, we only have one, the AHB. So there's an AHB agent which communicates through the AHB interface to cause stimulus to our memory. The test in a UVM test bench has configuration so that we can pass configuration objects down through the hierarchy, configuring all of the sub-level components like the agents and the scoreboards and the drivers and the monitors. And at the very top level in the test itself will be the sequence, the master sequence at least, that will generate and specify the kind of traffic that we want. So the top level sequence can be a relatively short class that can accomplish a lot of complex stimulus by virtue of leveraging the code that already exists in the agent and especially over there in the AHB interface. So, as I said, what's an agent? Well, it conglomerates together a number of subcomponents that together give us access to the bus. So notice the sequence is talking here to one of the built-in methods, one of the built-in class types in UVM called a sequencer. And this would be the bus agent, or in our case, this would probably be the AHB agent containing the AHB sequencer, and then a driver and a monitor that know how to talk on the AHB bus. You'll notice that the monitor has a broadcast port. This is a analysis port. If you're familiar with UVM, you're totally familiar with those, but it allows the monitor to broadcast to interested parties about what it sees happening on the bus. And that's going to be very important in just a moment as we get into the register model. So think of an agent as a term that's used for a hierarchical container class. It encapsulates everything that's needed to talk intelligently to one particular interface on the dot. It contains all the bus-specific sequencers, drivers, monitors, etc. And it provides the driver with transactions from that master sequence over there on the left that's up in the test class. Usually it depends on those tasks that I defined as being written over here in the interface block. And that allows the monitor and the driver here to simply call those interface tasks. It's a very structured, very organized way of doing things. And then, as I said, the monitor broadcasts what it observes. Okay, so most designs today have registers and memories within them. Of course, that's what we spend our time designing. So think of a simple design there with a bunch of registers and a memory. Now, these are all going to need to be tested and to be covered. Typically, the things we might want to do is read and write so we can access everything and everything's working through our target bus interfaces. We might want to analyze the register activity. We might want to do a scoreboard, for example, that can check the registers against a shadow device that contains shadow models of the registers, and we compare them to make sure that they stay in sync. I'm just giving an example here. We might want to collect coverage statistics on the registers, or initialize the registers or the memories just prior to starting a new test. All of these are things, of course, that the register model can do, including randomizing registers. One of the scary things about a design with lots of registers and lots of memories, of course, is that as the design progresses, we keep changing the memory maps. So anybody that writes a test that is hard-coded to, oh, what address this register was at on Monday, their test is almost certainly out of date on Tuesday when the next rev of the model comes out and somebody's had to change the memory model. So there's one very small, but still significant use of the register model. The register model is built from a set of base classes provided in the UVM library that allow us to build a model. It's script generated, so we don't have to write it by hand or anything, but it's an executable model based on the same hardware software spec that the registers and the memories themselves are defined using in your normal design flow. This means that whenever you change that hardware software spec, we can regenerate the register model. Now remember, the register model is only representing the storage elements in your design. That's why we call it a register model. We're not talking about any of the other functionality, just the storage elements themselves. So one way to look at the register model is that it gives us convenient access to the registers and the memories via one or more bus interfaces. But because the register model can be regenerated as soon as we change the hardware software spec, it gets the latest and greatest memory mapping. So we never have to worry about the changing memory addresses. All we have to do is make sure that we always ask the register model for the particular register. So let's say this register here was, RN was actually our control register. I could, of course, do a talk across the AMBA bus to get to address FFF blah, 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 which changes all the time. That's the thing we don't want to do. Instead, I can go to the register model and say, hey, register model dot control reg dot read dot write, various other methods that I'll talk about in a little while. So it provides a convenient way of accessing registers and memories via any number of interfaces that might exist on our dot for the convenience of those of us writing those test sequences. So the register model contains what I like to call a database. It's a database of all of the registers within the dot. I haven't said memories. I'll come back to memories in just a second, but all of the registers. Each register is represented twice in the database, okay? The first one is the desired value. The desired represents the value that we want to see in the hardware. So it's like a staging place. We can stage what value we would like to be transferred to the dot when we say go. The mirror is the best guess of what we think is in the hardware right now. I say best guess because it can't be 100% perfect, since the register model isn't aware of internal goings on within the dot. You might have a register that, like a real-time clock, let's say, going on inside the dot. How on earth would the register model know that the time is flipped and the real-time clock register has updated the current time of day to the nanosecond or whatever it is you're using? So it is possible for the volatility of the dot to not be reflected in the mirror register, but we can tell the register model, hey, update the mirror, and then we can use that mirror value for some decision that we might want to make. The memories, you notice I did not say are represented in the database because they're not. As a way to be more efficient, we don't contain or duplicate the memory, which could be a fairly large block, of course. We don't duplicate that with a desired and a mirrored version in the database, purely for performance. So instead, memories can still be accessed using the convenience layer, but there is no staging desired value or no best guess mirror value for memories. So the register layer then is a way of accessing that HDL top that I mentioned, which is containing our dot and some other models, from HVL top. Okay, now over here on the left, you can see I'm slowly building it up. We have the test that creates the environment, which instantiates the bus agent. And we could put a sequence here in the test, and that sequence could talk directly to the sequencer. And that would be fine. And that's probably what you're currently doing if you're not using the register access layer. But here again, now you have that problem. Over here, the register that we like to call by the user-friendly name control reg, it has to be referred to now by whatever its address is on our target bus. And of course that changes and it becomes difficult to keep up to date, et cetera, et cetera. So we're going to do something different. Instead, we're going to do away with this sequence to sequencer direct connection. And we're going to instantiate the register model that we can create from our hardware software script, specification, I'm sorry. And we're going to instantiate that. Here it is, sitting in the test, sort of above the environment class, if you like, or parallel with the environment class. And then we're going to build a translation layer, which is going to allow the register model to talk to the agent, or agents. Of course, there could be more than one if there's more than one bus interface into our DUT. One of the components we'll talk about is the predictor, and the other one is called the adapter. I won't get into them right now, but effectively what they do is they allow the register model to communicate in an abstract way with the particular bus agent that you connected it up to here. The register model has visibility to the predictor and the adapter and vice versa, and the predictor has access to the internal register database within the register model, but most importantly to the maps. And you'll understand why that's important coming up in a little while. So one of the key things that's cool about the register layer is it can allow a sequence that we write, such as this one in white over here, to access the onboard registers in the DUT using what we call the front door. Now, front door means we're going to go through the bus agent. So if this was a wishbone bus, we could, using this sequence, we could say, I want to do a wishbone write or a wishbone read of the control register. And that's a front door access, and it's going to take however many cycles, however many nanoseconds effectively it takes to perform the equivalent real-world wishbone bus access. But very cool thing about the register layer is it also supports backdoor access using the PLI. Now, if you've used the UVM library, you know that because it's package-based, using a system Verilog package, it is not allowed to do hierarchical references. And that's always been a bugbear about using UVM. For some people, you can't just reach out, but you can in the register layer because they've built in a PLI or DPI, I'm not sure which, I think it's the PLI that they use to get a roundabout way to get to the DUT registers, and you can access them hierarchically and directly without having to go through the quote unquote slower bus agent. So we have the choice of front door and back door accesses in the register model. All right, so let's talk a little bit about the register model itself, then how it's integrated, and then how we can use it. So it's implemented from 6 building block classes made available in the UVM library. If you think about any register in the design you're currently working on, there are, within any register, there are certain fields. So to represent a field, we have a base class in the library called UVM Reg field. Those fields get assembled into registers, and each register can be represented by the UVM Reg class type in the library. We have register files. Some people use them, some people don't. If you want them, you can. They're totally optional, but there's a UVM Reg file class for those. Of course, we assemble our registers. We tend to turn them into blocks, so you'll see we get to that in a second. But first, we also might want to add in some memories, so we can extend from the UVM Mem base class for that. Then we have the map, which represents perhaps just one of multiple buses that can access these. You know, we might have multiple interfaces feeding into our DUT, but let's assume it's just one for now. So we will have a map, and we'll declare that map in a UVM map based class, which of course allows us to define what the memory locations are for all of these registers. Then we can put those in blocks, and we can assemble multiple blocks into macro blocks, et cetera, et cetera, et cetera. And the whole thing allows us to define a register model. Now, register models are created by script, as you'll be glad to see in just a minute, because remember, they're reading in the same hardware software spec, which might be an Excel spreadsheet, or it might be some other internal format. And most companies that don't have a standardized way of feeding generating the register model through your chosen EDA vendor's tools, like maybe you're a Mentor user, maybe you're a VCS user from Synopsys, they can import certain file formats each. But sometimes you'll take your own internal format and convert it to a standard format and then feed that to the tool. But one way or the other, it's integrated into, it's read into the tool, and the tool spits out something like this. So I've dived into a register model here for a SPI register design. Just to pick one particular register as a quick example, this is a class control. So this is our control reg that I've been using as an example. Notice it extends from UVM reg. Then we declare the UVM reg fields inside there. Now, I'm not going to go into any detail because we don't have enough time, but basically you can see that I have gone to the trouble of declaring the register fields. That's where all of the heavy lifting, by the way, happens, because it's the fields that have certain specific bit widths and all of the rest of it. There's a standardized constructor, okay? I think I've already mentioned those. And here's where we then go in the next in the next method, we build our register, this control register. And you notice in this build method, we declare we call create for that register field, and we configure that field. So you'll notice all of the low-level ugly detail here about whether the field is read-writable, how many bits it's wide, what its reset values are. Aren't you glad this is all script generated and you don't have to type this stuff in? But I think I can very, very briefly give you the image that this is a fully detailed model of the hardware structure, register structure, and field structure within the register model. Then we might have a register block. This is perhaps the top level block, or it could be a lower level block if we have partitioned the SPI design. But whether it's the top or the lower level, you'll notice that it's a class that extends from UVM reg block, which is another of those base classes. And here we instantiate all of those registers, including, in dark here, the one that we just looked at, the control reg. We also declare the map. And as you'll see here, we, having created that register and built it and configured it, we then create the map and we add these registers to the map. So here's the control reg being added to the map. And so you don't need me to tell you what these mean. RW means the APB bus has read-write access to this control reg, and you'll never guess what that is. That's the address on the APB bus of the control register, address 10. Okay. One interesting thing at the bottom there is lock model. Just very briefly, lock model is an interesting thing. Remember, what we're creating here is a runtime model of our hardware, but it's not precompiled and saved as a binary or anything like that. It's a real live model. So we use lock model as a way to disable all of the API methods here so that you can't accidentally or on purpose have self-modifying hardware during the simulation of your RTL code. Wouldn't that be fun? Okay, so we've used our script and it has spat out a register model. Now we have a model that we want to integrate into our UVM test bench. So here's the UVM test bench, very much the one that I showed you earlier. We're perhaps used to seeing this sequence talking directly to this sequencer so we can do our own, front door accesses, but we've decided we don't want to do that anymore. We want to use the register model. So we instantiate the register model that we generated with a script, and then we build up the adapter predictor. These are the adaption layer, as they're referred to in UVM, that allow the register model to talk to a particular bus agent. So you'll notice that the predictor has handles to the adapter and the map, and I'll explain how that works in just a minute. But also you can see that the arrowheads here in these little dotted lines are bidirectional because the register database also has access to the predictor and the adapter. The register model does, and I'll explain how that all works. But first, let me describe those two subcomponents. The first one is the adapter, and its job is to translate between a generic or abstract base class representation for the register model to the specific transaction object type that our bus uses, maybe AMBA or Wishbone or something like that. So the adapter is a class we write that extends from UVM reg adapter, a base class in the library. And all we have to do in there is override two methods. There's one called bus to reg and one called reg to bus. And the reg means the generic register model transaction item type, and bus means whatever your target bus is. So you might, if you're an AMBA bus designer, you think of this as the reg to AMBA. It still needs to be called reg to bus, but you can think of it that way. okay? Bus to reg does the opposite. Now, each of these methods, as you can see their signature down here, then need to specify both the abstract register model type and the target bus type as well. So first of all, in either case, you can see the generic transaction type, UVM reg bus op. That's the generic type predefined by the register model. We need to translate that to and from some particular transaction type for our particular target bus, maybe an AHB, wishbone, whatever our transaction type might be. In this case, we're always referring to it in the library code here using the UVM sequence item, which is, of course, the base class for the transaction type that we've created. Here's that generic register transaction type, UVM reg bus op. And again, without going into too much detail because of our limited time, it has an address field and a data field. Duh, pretty obvious. We want to access this address, and data is the value we're going to write to it or read from it, etc. Kind is the kind of transfer we're going to do. Notice we can do single word reads and writes, and we can do burst reads and writes. N bits is the number of bits we're going to transfer. Byte enable tells us whether this bus is byte enabled or not. You know, some buses are, some buses aren't. And status is a return value that will tell us how we did. UVM is okay, UVM is not okay, or UVM has some unknowns in it. So a quick example, let's say we have an APB sequence item for our APB bus. So we have adder, data, write, enable, and delay. So what we need to do is create a reg2 APB adapter, which extends from UVM reg adapter. Here it is, we're registering it with the factory so that we can use the factory to create this. Standard boilerplate UVM constructor. And we override the reg to bus and the bus to reg methods with some code in here to simply translate, okay, between the generic reg bus op, like I show here, and of course the specific values in the APB sequence item fields. So that's really it. That's all I have to do with the adapter is write those two methods. Second part is the predictor. So now we've inserted the adapter, and it's going to allow the register model, for instance, to translate a generic reference to a specific register to a target transaction, to create a target transaction that this sequencer would be able to understand. And the way it works is the register model will effectively behave like a proxy for us. On our behalf, it will talk to our target bus agent. You'll see that in just a second. The second part, of course, is the predictor. This is simply instantiating directly a component from the library called UVM reg predictor. It's parameterized with the type of this analysis export. So we need to specify what that is, which of course needs to match the type coming out of the bus agent. So if this is an AMBA bus agent, etc., then presumably this analysis port is broadcasting AMBA transaction objects. And so that's the type that we've specialized the predictor to expect. The predictor also needs pointers to the map and the adapter, and you'll see why in a minute. So let's see if we can walk through how this works. So up in our sequence, instead of creating a AMBA bus transaction object and going direct to the sequencer and saying, here, take this and perform this operation, instead we're using the register access layer as a convenience layer on top of our hardware. And of course, remember, one of the things it lets us do is backdoor accesses, which we wouldn't be able to do otherwise. So from our sequence, I hope you can see this faded red arrow here. From our sequence, we're going to go to the register model. We're going to say register model dot control reg dot, do something. Let's say write. I'm saying I want to write to this control register. So now the register model internally from our call from the sequence has created its own generic transaction description that says I'm supposed to do a write to this register with this value. Now the register model it knows what address that register sits at because it looks it up in the map. But of course, it still only has this generic transaction type. So the next thing is to go to the adapter and translate from the generic transactor type to the specific transaction type for our particular bus agent. So the adapter, those two methods, reg to bus and bus to reg, right? We know we can call the appropriate one of those, and we've generated a specific bus transaction type. Now the register model is free to create a proxy sequence and talk to the sequencer in the bus agent and give it that transaction type. So that's what happens next. The register model talks to the sequencer and says, do this. The sequencer takes the incoming transaction and effectively, using the driver and the bus interface, writes to that register on the AMBA bus, let's say, or the AHB bus. Now, that's it, right? We've just performed the write and everybody's happy. Except think about what has happened here. We wrote to the register in the register model, and then we had the register model talk to the agent and cause the real hardware to be written. But we'd like some confirmation of that. So while there's activity on the bus, the monitor here has been observing that. The monitor watches the bus and isn't even necessarily aware that it was the same agent, that it was the driver who caused that activity. It doesn't matter. It could be somebody else on the bus. The monitor says, hey, somebody wrote to address 10 on the bus. And so what the monitor does is it captures that information and broadcasts it to anybody that's interested, okay? And that goes up here to the predictor. Now the predictor has received a broadcast from the monitor referring to an access on the bus. The predictor, it doesn't matter whether the predictor knows or doesn't know that it's come from our sequence and it's coming from our agent. It could come from somewhere else even, but the predictor now has access to the map and the adapter to do the translation in reverse. It can look up what that address represents, which you and I know is the control register. It can use the adapter method to transfer from the AHB back to a generic bus operation. And finally, it can update the register in the register database. So ideally what happens here is the sequence might write to the desired register, but the mirror won't be updated until the monitor and the predictor have actually seen the access on the bus. And that's basically the way it works. Now, I could bore you by going through all of that again, but instead I just put those here on this slide so you'll be able to refer to them again if you want. So what are the advantages of all of this? Well, first of all, the test author doesn't have to remember the changing addresses for every resource on all of the different buses on our DOT. The register model is always up to date with the design because it's script generated, and as soon as the hardware software spec changes, we can regenerate and have an absolutely up-to-date register model. The register model works as a convenience layer on top of registers, memories, etc., giving us convenient access. Now, I've only scratched the surface of the convenience capabilities of the register model, but what I've shown you is pretty useful too, even just at this level. The predictor and the monitor independently monitor the bus for activity. That's very important if you think about it. We have independent confirmation that the traffic on the bus did exactly what we think it did, because we can compare the desired register with the mirror register and say, well, if they're the same, then I know the bus transaction actually occurred. And the register model updates the predictor even if the test author didn't originate that change. So even if there was some other agent on the bus changing that register, our register model would be updated because the predictor doesn't care who generates the traffic. He just monitors it and says, I want to see what has changed. So now we're coming to the third part of this session, where I wanted to talk about how do we use the register layer. So you have found a way to get your hardware software spec fed into a tool, a script that can generate a register model for you. You have integrated that register model by typically instantiating it up in the test class and by hooking it up using the adapter that you've written those two methods for and the predictor that you've instantiated. And now how do you make use of it? I gave you the silly example of register model dot control reg dot write or dot read, and those two are indeed API methods, but there's a lot more. So we have now got a sequence on the left, and we have the register model. I'm just showing the database here, but we have the register model in between, and we have the hardware over on the right. The register model allows us to access the hardware registers front door and back door. We know that. So it provides a whole bunch of methods that allow us to do that. A set of methods to do both front door and back door. They can access memories, they can access the registers, they can even access the fields within those registers. The methods Some of them work backdoor, some of them work front door, some of them do both, okay? I don't have time to go through all of them, but basically you can see from this diagram that we have a method called get, which retrieves the desired value. So your sequence could say, I wonder what's in the desired value for this particular register. So if I said in my sequence, if I said register model.controlreg.get, it would return the desired value. If I said register model.controlreg.set, I'd be setting the desired value. No effect on the dot, but just on the registers within the database. Get mirrored value retrieves the mirrored value. Predict is what we use to write the mirrored value. Read and write and peek and poke, they jump right through the register model and they go straight to the dot and they access the hardware. Reading and writing does front door or back door accesses, and peeking and poking would be backdoor accesses only. And then we have two other methods, update and mirror, that I won't get into, but they involve manipulating the dot based on the values in the database. So let's look at an example and see how this all can come together. So here's a base class sequence that we'll be using to extend, we'll be extending from it to develop a number of different sequences to test our SPI bus design. So I have a SPI bus base SEQ model. Notice it has a handle to the register model because we're going to have to be able to say SPI RM dot control reg dot write or read or whatever. So that's how we're going to do it. How you get that register model handle, well, that depends on how you want to do it. One way to do it would be here in the task body of this base class sequence. We might go to the UVM configuration database and do a get of the SPI reg block. That's the name I've given it when I wrote it into the database, and store the value in SPI RM. So in this, here's an example of how we stored the register model handle into the configuration database, and here the SPI base class is retrieving that. So any sequences that extend from this can just accept the fact that SPI RM is actually a valid handle to the register model. Now let's look at one of those sequences that extends from SPI bus base sequence. It's a control set sequence. You can tell from that we're going to set the control register in this sequence. So here's the body of this sequence. And notice I'm asserting a SPI register model dot control reg dot randomize. So I'm randomizing the values in the register perhaps. Then I'm setting the interrupt enable, the IE field in the control reg. Notice SPI rm.controlreg.ie.set. Set is the one I mentioned very quickly, I know, but it goes to the desired register. So what we're doing is we're setting the desired value. That's just in the database. It hasn't affected the dot. We also go into the control reg and we set the go busy to be a 0. Then we call update, and update is a method that says update the hardware to make it look the way we've programmed the desired registers. So it takes all the desired registered values and copies them over to the hardware. And you can specify to use front door, which I'm doing here, or even to say back door, in which case you could specify all the desired registers and then instantaneously, boom, transfer them all into the dot. That's a very nice, convenient way to quickly initialize the hundreds of registers in your dot. And then just as an example, I'm following that up with a get, which is retrieving the value of the desired register. I'm not sure why I did that, but basically it's just an example of a call. Now, one of the things that I'm often asked by people is if I want to learn to write better UVM code, in particular, if I want to learn how to use the register model and the register access layer, are there some good examples? And there are. I'm sure you've got people at your company will have good examples that they can share with you. But if you're starting from scratch, one of the things I like to recommend people look at is a set of built-in sequences that are distributed as part of UVM, as part of the register layer package, that give you access to the registers or the memories within your design. And they are convenient because in 3 lines of code, and I'll show it to you in a second, in 3 lines of code, you can do complete reset tests on every single register in your design. Not bad for 3 lines of code. So the UVM library defines a set of these test sequences. And I like to point them out to people because, first of all, people often don't know they're there. But secondly, these are very well written and they're very well documented internally. So they can teach you some very cool stuff about how to use the register layer. For example, they allow you to do basic tests on the registers and the memories. Things like, has the register reset correctly? I can validate the read and write paths, so I'm able to access this memory from all of the following buses via all of the following paths. This can be used for quick sanity checks, or, I mean, at some point, somebody's going to have to write this test. Why not leverage the built-in sequences to do it? Here's the current list of these tests. We've got single bit bash, right? We've got bit bash, we've got single access. Memory access is shared access for both registers and memories. There's a lot of them here. There's the first one, the hardware reset, that verifies that the registers are resetting correctly. So I'm going to dive into one of those quickly as an example, just to give you a feel for what you can do. But before I get to that, let me also expose you to another very cool feature of the UVM register layer. The UVM register layer was written to be introspective, which means, unlike a lot of the rest of UVM, the register layer has the ability to tell you things about itself. Introspection means code that will answer questions about itself. It can identify its own characteristics. So in the case of the register model, this can be extremely handy and save you a huge amount of time. If you wanted to write a generic test, and let's face it, they don't come any more generic than these examples here. If you said you wanted to write a test that verified the reset capabilities of every single register in the dot, okay, where do I get a list of all the registers? And where do I get a list of all their memory locations? And how do I know how many buses there are in this particular design? How many bus interfaces onto this dot? All of that, I could write a test with the basic knowledge, yes, but then somebody changes the design, somebody changes the number of interfaces. Now my test has to be completely rewritten. But introspection changes all of that. For example, how about find blocks? This will return, okay, this will return a queue. Here we go, UVM reg block blocks. It's a queue, and it will return a queue with a handle to every single sub block within the register model. Get root blocks will tell you the top level blocks. Obviously, for most of us, that would be just one, but there might be more than one. Get blocks. How about get maps? This will return a queue that is a list of all of the maps within the register model. In other words, a list of all of the buses that are defined in the register model as ways to access the registers within our device under test. If you have a dot that has 3 USB ports and an AMBA bus and an I2C for debugging or something like that, well, this will return handles to all of those things. Similarly, we can get all of the fields within a register, and there's lots of other things too. So with the basis of that idea, that concept of introspection, I'll show you some cool code in just a second. But first, let's see how we would use one of those built-in sequences. There's a few more lines of code than just 3, but that's total boilerplate, like raising an objection and dropping an objection, okay? The 3 important lines of code are in bold here. The first one says create that sequence. So this is the UVM reg hardware reset sequence. That's one of the built-in sequences in the UVM library. I've created it now. Then I have to tell that what its register model handle is. So each of these sequences has an internal handle called model, and I have to point that to the register model that we're using. In this case, mdma system block.dma top happens to be the name of it. And then we say mseq.start and pass in the sequence handle like we always would anyway. And this will now run through the entire structure of the mdma system block, finding every single register and testing it. Not bad for 3 lines of work, 3 lines of code. Okay, so let's look at another one of these built-in tests. The reset one is interesting, but it's not terribly elaborate. I've picked a slightly different one that's more interesting because it's the UVM reg shared access sequence, all right? This extends from UVM reg sequence. Now, this isn't code that we wrote. This is pre-written. It's distributed as part of the library. But basically, I wanted to point out a few things in here. First of all, it has a body task that defines some various Scratch variables that are interesting, but you'll notice it defines a set of masks, a queue full of masks, a queue full of fields, and a queue for the maps. These are the different memory maps that this register model knows about. Now, we don't know when we write this sequence, the author of this sequence didn't know how many fields you would have in your design, didn't know how many maps you would have in your design. So this is where introspection comes into it. First of all, there are registers within this design that appear on more than one map. Those are the ones we're testing. This is the shared access sequence. But there are registers that only appear on one map. So we'd like to filter those out, right? That's a pretty obvious one. So how about if we said if reg, so we have a list of registers, and we say if reg.getNmaps is less than 2. GetNmaps is an introspective call that any register can support, and it tells you how many maps it appears in. And if it's under 2, we don't want it, we're not interested in it for this particular sequence. See how useful that is? How about reg.getMaps? So it will continue on because we didn't need to exit because there is more than one map. So let's get a list of those maps, and I'm holding those in the maps directory and the maps queue. And you can see here straight away a very, very convenient way of accessing this information by using the introspection, getNmaps and getMaps. I apologize, that's going to stop in just a second. I forgot to turn my phone off. So continuing on, how about we say reg.getFields? So we want to test this register, so we'll retrieve all of the fields and store those in the queue called fields. And now we can do a for each on those fields, so we can step through each field. Notice we don't know what the specific fields are. We simply retrieved a list of all of them into a queue, and we can process that queue using a for each. For each of those, we can get their least significant bit position, the number of bits wide this field is, check if the fields have a known access map. In other words, the policy says that we can access it. It might be read only, it might be write only, something like that. And again, without going into the details of what the test is trying to do here, we can mask out the fields that we're not allowed to access, and we can continue on and complete the testing for every single field and for every single map. So just a really, I know, 50,000 foot view of how introspection in the register access layer gives us the ability to write very, very useful code in what, a dozen lines of code that could access a generic design with hundreds of registers, dozens of memories, etc. I think I already said that. So we've reached 11:48 here, my time on the West Coast, and it's time for some questions. Anybody have questions they want to ask? I don't see any, but I'll give you a minute to ask any if you have some. Or if anybody would like me to go back over something, we have a little time. I'm happy to run through something again if it would help to refresh it or explain it in a different way. Nope, no questions. Okay, so let me move on here. I have a few other slides I'd like to show you. First of all, I'd like to mention that Hardent has some on-demand verification training courses available. They were developed and launched just earlier this year. We have on-demand training in System Verilog for verification and in an introduction to UVM. These offer flexible self-paced learning, so you just purchase a 30-day access and you can go through the training videos with the labs, and it's all based upon the in-person training classes that we designed at WHDL and that we teach. Of course, we offer those training classes too, of course, but for some people, limited number, inability to travel, etc., an on-demand verification training can be a very useful way to go too. And there's a special introductory offer. If you sign up for this, you get to attend 3 follow-on online group Q&A sessions with me or with somebody else to answer your questions and go through other examples and discuss other issues that arose for you. Secondly, I'd like to point out the current verification training schedule for Hardent classes. Now, this is a set of classes that are on the schedule, and they're in various, excuse me, various locations, although some of them are on demand, obviously, so those are on the web. But you can always check at hardent.com/training to see the full schedule. And the class locations are across Canada and across the US. And of course, we can hold any of these classes at your site if you wish. Just get in touch with us, hardent.com/training. You can see the upcoming classes in Q1 of 2019. We'll be offering our first portable test and stimulus standard, PSS classes, using the Brecker and Cadence tools. We'll offer system Verilog for verification and also introduction to UVM, as well as an advanced UVM class. There's also a number of other classes that are available. These are all online, and these are all available in, as you can see, various different topics. The two I'd like to particularly point out to you are the embedded system design for the Zinc UltraScale plus MPSoC, and the following one, the embedded design with PETA Linux tools. These are shown in red here, December 10th to 12th and December 13th to 14th. These have already met their quota. People are already signed up. These classes are confirmed, but there's still a few spaces available. So if you're interested, that's a way to find a class that you already know is going to happen. Again, once again, go to hardent.com/training, all right, to see a full schedule of the training classes that are available. So I still don't see any questions, so I'm going to wrap up at this point. But I would like to point out that at the end of this seminar, there will be a very, very brief, 3 seconds, that's all it takes, a 3-second survey at the end. If you would just answer one question for us, and 3 seconds is all it should take you, and we would really appreciate it. One more time, you can always reach us at hardent.com. You can email us, info@hardent.com. And the phone number is 514-284-5252. And with that, I'm going to hand back to Marianne.